at an application of a linear function today, shall we? And let's start out with a phrase. Suppose I were to say y varies directly as x, all right? As x, or else suppose, for example, we were to say y is directly proportional, all right? Proportional to x. And looking at these two phrases, there's a way in which we interpret this in a mathematical sentence. And does anybody have any feeling for this? I think we looked at it once before in our Algebra 1 course. And suppose then we were to say y is equal to m times x, in which we have here y varies directly as x, in which this number m is given a special name. We call this a constant of variation, or else a constant of proportionality. We also refer to it as that. Now, this, I think if you look at it, is a special case certainly of a, what kind of a function? Of a, Don?
Linear.
Of a linear function. We have here y is equal to mx plus b, where the number b is equal to 0. And if we were to look at a graph of this, the fact that b is equal to 0, I think you will agree, must be a line which is going to pass through the origin. And let me take some point, any point on this line. Suppose we were to call the coordinates x sub 1 comma y sub 1, and some other point on this line, x sub 2 comma y sub 2. All right? Now, looking then at our graph and at our equation, at this formula, since this point x sub 1 comma y sub 1 is on the line, therefore those coordinates must satisfy the equation. Is that right? Therefore, y sub 1 must be equal to m times x sub 1. Similarly, y sub 2 must be equal to m times x sub 2. Is that right? Now, let's look at this, and if we were to divide through by x sub 1, where it is not equal to 0, we have it equal to m. And if we were to divide this through both sides by x sub 2, where x sub 2 is not equal to 0, it's equal to m. Now, looking at these two sentences, what then can we say but that, Tom?
Y sub 1 over x sub 1.
Therefore, y sub 1 over x sub 1
Equals
is
y sub
equal
2.
to
Y sub 2 over x sub 2.
y sub 2 over x sub 2. And we have here what we call a proportion, all right? A proportion, T-I-O-N. Now, let's then look at this proportion. Perhaps I can repeat it up here, in which we have y sub 1 is to x sub 1 as y sub 2 is to x sub 2. And there's another pattern that people write, that mathematicians write, in which we write it as y sub 1 is to x sub 1 as y sub 2 is to x sub 2. All right? Now, the fact that these two numbers are in the middle here, we have given those a special name. And does anyone remember, Bill?
Those are the means.
Called the means. And of course, those then on the outside here, we refer to those two numbers as the, Michael? As the extremes. All right? And we call these the extremes. Now, let's then write this proportion down again, in which we have y sub 1 is to x sub 1 as y sub 2 is to x sub 2. And if we were to look at this proportion, if we were to multiply both sides through by x sub 1 times x sub 2, all right, x sub 1 over x sub 1 is a name for 1, and we'll have x sub 2 times y sub 1. And over here, x sub 2 over x sub 2 is a name for 1, and we'll have what? Y sub 2 times x sub 1. Is that right? Let me then write it as x sub 1 times y sub 2 is equal to x sub 2 times y sub 1. And notice here then that our means are these two numbers, is that right? And our extremes then are these two numbers. And what then does this statement say that we have written here, Brenda?
Product of the means is equal to the product of the extremes.
Good. The product of the means is equal to the product of the extremes. Okay? Well, let's then look at the various types of proportion, or rather the various types of functions, linear functions that we have been concerned with. Let me call this idea number 1 and give it a name of direct variation. All right, and then if we then were to look at this, let's call this the various types of linear functions that we have looked at thus far, the various special cases of them, really. The first case perhaps might be the general pattern, the y-intercept pattern of y equals mx plus b. And let's just call this one a linear function. And then suppose, for example, we had y then is equal to b. If you remember, this one was called a, what name did we give this, Bill? This is a constant function in which its graph is going to be a line which is what? It's going to be horizontal. And then if we looked at a special case such as y is equal to x, what name did we give this function, if you remember, Doug?
The identity function?
We referred to this one as the identity function, and now in fact we have this case of y is equal to m times x, in which the identity function is simply a special case of it. And if we had to give this function a name, what then would we call it? And on the basis of what we had just been saying, let's decide to call this one, Brenda,
Direct variation.
a direct variation function. Very good, a direct variation function. And I think these are the four types of cases that we have considered thus far with respect to a linear function, and in fact they're probably all of the linear functions that one ever has to look at. Well, let's come back to this idea of a direct variation, and let's look at a few examples, one or two of them at least, in which we have if y varies directly as x, and y equals 12 when x equals 3, find y when x equals 5. All right? Now again, as soon as we see that y varies directly as x, we may write this formula, y is equal to m times x. For some particular value of y, let's call it y sub 1, we have a particular value of x sub 1. And then for another value of y sub 2, we have a particular value of x sub 2. Is that right? And then doing as we have before, if we were to divide through by that number, and we're to divide through by an x sub 2, it's equal to m. Therefore, what is our conclusion? But that, Peter?
Y1 over x sub 1
Y sub 1 over x sub 1
equals y sub 2 over x sub 2.
Y sub 2 over x sub 2. And now notice here, in this proportion again, from the data that is given to us, we know y sub 1, call this number, and x sub 1, and we would like to find a y sub 2 when we know x sub 2. So how many of these four numbers do we know? And we would certainly know three of them, therefore we can find the fourth. And let's just make a substitution here. Y sub 1 is 12, and x sub 1 then must be equal to what number? 3, as y sub 2, which we do not know, is to 5. And of course 12 over 3 is 4, and therefore y sub 2 is equal to 20. Okay. Let's look at another problem in which we have here the distance to a lightning bolt is directly proportional to the time elapsed from the instant the bolt is seen to the instant the thunder is heard. Now, if you hear the thunder 9.6 seconds after you see the bolt is approximately 2 miles away. If you hear thunder 4 seconds after you see the bolt, approximately how far away is the bolt? All right, there are a lot of words there. So let's get right back here to the first sentence in which it says the distance to a lightning bolt is directly proportional to the time elapsed. So who then can give me a formula for that? Let's call D the name for the distance, and T, say, be the name for the time, Kirby.
D equals m times t.
D then is equal to m times t. Is, I think, a formula which would then interpret this direct variation that we have in this problem. All right, let me then simply go into D sub 1, say, is to T sub 1, as D sub 2 is to T sub 2. And again, of these four different numbers, how many of them do we know in this problem? We certainly know 3 of them, and let's then simply make our substitution. Coming back here to the problem, if you hear the thunder 9.6 seconds, and so that then would be our time of T sub 1 of 9.6 seconds. The lightning bolt is approximately, what? 2 miles away. So there then is our distance. And then the question asks, what? Approximately how far away is the bolt? And that's our D sub 2 number, which we do not know. Is that right? Whenever we hear the thunder 4 seconds after we see that bolt. So this is the T sub 2 then must be 4. And let's just work with this and see what we have. Let's see, we have 9.6 times D sub 2. The product of the means is equal to the product of the extremes. D sub 2 then is 8 divided by 9.6. And let's see, some number will divide there, such as what?
12.
Well, let's see now. 8 will divide 1, and 8 into 9.6 goes
1.2.
1.2. Is that right? which is indeed a name for 10 over 12. Is that right? Multiplying through by 10, and of course that's a name for 5, 6. Well, let's leave our answer in that pattern. And this then would be what? With respect to the unit of measure that we are talking about, the sentence that we would like to make, which is our English conclusion, is what? That the boat, Doug?
Is 5/6 of a mile away.
The boat is 5/6 of a mile away after 4 seconds of hearing the thunder. Okay, well, I think that's all that we should do for today's lesson. So let me give you your homework assignment.